All right, let's go ahead and get started so that we can try to get out of here at a reasonable time where everybody is able to get a place to park out there. They've got some kind of the Cirque de Music thing, Wonderland over at Brick Reading, and man, parking is at a premium tonight. Same as usual, we'll just go through these set of practice problems just one at a time. And if you want to see that one, just say yes. If you don't want to see it, just don't say anything. Somebody else might want to see it. If nobody says anything, we'll just move on to the next one. So, let's see. Number one. Yes. Okay. So number one says one significant difference between gases and liquids is that what? And so A says a gas is made up of molecules. Okay, that can be true, but can liquids be made up of molecules? Of course, water's a molecule, so that's not a significant difference. Gases assume the volume of its container. Okay, is that a significant difference? That is the difference. Okay, a gas always fills the container that it's in, whereas liquids can only fill a container up to that liquid's particular volume, and it can't change its volume like a gas can. So that's why B there is the correct answer. If we look at the other ones, gases are always mixtures. That's not true. You can have pure oxygen. That's not a mixture. A gas may consist of both elements and compounds. That's true, but a liquid can as well, so that's not a difference. Then E, of course, is not correct because we saw how some are not correct. So good. Questions on that one at all? All right. Number two. Yes. Yeah. Okay, so number two says that the following blank is a correct statement of Boyle's law. Okay, so Boyle's law is the law that deals with the relationship between pressure and volume, and pressure and volume are inversely proportional. So as one goes up, the other goes down, and vice versa. So that means that pressure times volume is always going to give you the same value. So pressure times volume is equal to a constant. So the correct answer there is E. So PV is equal to a constant. That's for a given closed system. As soon as you open the system or you change to a different gas or something, or you start changing the temperature, then everything is off there. So that's assuming everything else is still a constant. All right, number three. Yeah, okay. So it's a sample of gas, 24.2 grams, initially at 4 atmospheres. Was compressed from 8 liters to 2 liters at constant temperature. After the compression, the gas pressure was what atmospheres? So this one includes a mass. The mass that they have in there, that 24.2 grams is a decoy. We don't need that at all. All we're doing is taking a system and changing its volume. So we can use P1, V1 is equal to P2, V2. And so we've got an initial pressure at 4 atmospheres. So we know that P1 is equal to 4. We know that V1 is 8. We know that V2 is equal to 2. We're looking for P2. Okay, so we plug in what we know. So we have 4.00 times 8 is equal to P2 times 2. So you have 32 is equal to 2 times P2. So P2 has to equal 16, and the unit that would be left is atmospheres. Okay, any questions on that one at all? So P1, V1 equals P2, V2. Got to keep an eye out for decoy data in some of those questions there. Now let's see. Number 4. Yes. So a balloon originally had a volume of 4.39 liters at 44 degrees Celsius and a pressure of 729 torr. The balloon must be cooled to what Celsius to reduce its volume to 3.78 at constant pressure. So we don't really care what the pressure is because the pressure is being held constant there. And so what we're really looking at is a relationship between volume and temperature. And if you remember right, we have V1 over T1 is equal to V2 over T2 here. Our V1 is 4.39 liters. Our T1 is equal to 44 degrees Celsius, which is equal to, what do we got for, there we go, 317 Kelvin. Our V2 is equal to 3.78 liters, and we're looking for our T2. So we plug that in, we get 4.39 liters over 317 Kelvin is equal to 3.78 liters over our T2. And we solve that, we end up with a T2 of 273 Kelvin, which when you convert that to Celsius, you get 0 degrees Celsius. So for whenever you're doing these kinds of problems with temperature in there, using gas law stuff, the temperature has to be in Kelvin. Even though the problem gave you a temperature in Celsius, and it asked for a final answer in Celsius, okay, you have to convert it to Kelvin, do calculation in Kelvin, and then convert it back. It's kind of like grams and moles. We can't convert, we can't do stoichiometry problems in grams. We've got to convert to moles first, then do the math, and then convert back to grams. With temperature, we've got to do our calculations in Kelvin, and then do the math, and then convert back to Celsius. Okay? Questions at all on that one? All right. Number 5. I'm not even going to ask. 5 is kind of a weird one. It involves Avogadro's law, and that was presented in the book. I didn't do that one in class, and to be honest, I don't know why. I've got to change my notes on that one. So Avogadro's law just gives us a relationship between volume and the number of moles, and it looks a lot like some of the other laws we did, where if pressure and temperature are held constant, then we have the relationship of N1 over V1 is equal to N2 over V2. Basically, if you increase the number of moles of gas, then you have to increase the volume to keep pressure and temperature the same as well. Now, the strange thing here is we're not given the number of moles, we're given the number of grams, and so it's like, well, we need to convert that to moles. The problem is we have no idea what gas it actually is, and so we have no way to convert it into moles, but that's okay, because we can actually replace our number of moles there with our mass. Because it's the exact same gas, I would just be dividing the number of grams by the exact same number, and I'm still going to have the same ratio between those numbers. So it's okay to use mass here. That's what makes this a little bit of a confusing problem. So we can actually use mass here for this one. So for N1, we can say that N1, if we wanted to, we could say it would be equal to 50.75 over, we'll just call it molar mass here, and we know its volume is 10 liters. And then we want to know our second one, N2, so that would be equal to 129.3 grams divided by the molar mass. That would give us number of moles. And we're looking for a V2. So if we did this, we would have N1 would be equal to 50.75 divided by the molar mass of the gas over V1, which would be 10 liters. That's going to be equal to 129.3 grams over the molar mass. And all of that divided by my V2. It looks like I've got two unknowns because I've got V2 and I've got molar mass there. There's some seats down here if you guys need somewhere to sit. If you don't mind sitting up close, I don't spit much.
So these molar masses here actually cancel out.
Okay, yeah.
You
Sorry about that. All right, so the molar masses there actually cancel out. So all I'm left with is V2 and the masses in grams, and that's okay. Sometimes that happens. So when we solve this for V2, we end up with 25.5 liters. At least I hope that's what we end up with. Is that an answer on there? Yeah, there it is, E. It sounds a little bit weird, but I don't think I'd try not to give you one quite that strange on the exam. All right. Questions on that one at all? Is that making sense? Okay. Number 6. Yes? So, amount of gas that occupies 60.82 liters at 31 Celsius and 367 millimeters of mercury is X number of moles. So this is just an application of our ideal gas law. So we have PV is equal to nRT. We're looking for number of moles here, so we can rearrange this. So it's going to be N is equal to PV over RT. And we've got to do a little bit of converting here. We've got a volume that's equal to 60.82 liters. That's fine. My temperature is equal to 31 degrees Celsius. That's not okay. I've got to convert that into Kelvin, so that's going to be 304 Kelvin. I've got a pressure that is 367 millimeters of mercury. I've got to convert that into atmospheres by dividing by 760. And when you do that, you get 0.48 atmospheres. And then my R, of course, is 0.08206 liter atmospheres per Kelvin mole. That's just our constant there. All right, so we're solving for N here, so we just plug everything in. So we have our P times our V, so we have 0.48 atmospheres times 60.82 liters, all over our value for R, 0.08206 liter. This is one thing I hate about doing gas law stuff, is writing out all the units for R. And then over T, which is 304 Kelvin, and we can see our units cancel. Atmospheres cancel, liters cancel, Kelvins cancel. I'm left with 1 over moles in the denominator, which becomes moles in the numerator, so that's good. I'm looking for moles. And when we plug in all of those numbers, we get 1.18 moles for that one. Any questions there? All right, good. Number 7. Yeah, 7 I had a lot of questions on, people coming to my office. So it says, for which of the following changes is it not clear whether the volume of a particular sample for an ideal gas will increase or decrease? So the way to do this problem is to look at the changes that they propose. For the changes that they propose, they'll either both increase the volume or both decrease the volume. And if they both do the same thing, then you know what's going to happen. But if one does one and one does the other, without the values, it's hard to know which has the greater magnitude and which will win. Will the increase win or will the decrease win? Okay, so that's what we want to look at. So if we look at A, if we increase the temperature and decrease the pressure, okay, what effect on the volume does increasing the temperature have? Makes the volume bigger, right? Think of a balloon. If you heat up a balloon, it's going to get bigger. What if we decrease the pressure? Balloon's also going to get bigger. Okay, so both of those things would make the volume get bigger. Increase the temperature and keep the pressure constant. Okay, if we increase the temperature, volume will increase. And keeping the pressure constant has no effect. So if we do both of those things, we know that the volume will increase. Decrease the temperature and increase the pressure. If I decrease the temperature, what's the volume want to do? Wants to shrink. And if I increase the pressure, that also makes it want to shrink. Okay, so those two things both make it want to shrink. So we know what's going to happen there. Increase the temperature and increase the pressure. If I increase the temperature, what's the volume want to do? Wants to get bigger. If I increase the pressure, what's the volume want to do? It wants to get smaller. Which one's going to win? We don't know. We don't know which one's going to win because we don't know what kind of increases. You may increase the temperature by 1 Kelvin and increase the pressure by 80 atmospheres. The temperature ain't going to win that one, or vice versa. So there's no way to know without the values. And so that's why D is the answer there. Okay, because they're two conflicting directions and we don't know the values. Okay, good. Now let's see. Number 8. Yes. Let's see if I can get this one. I should be able to get this one on this last line here. Let's see. So number 8 says density of ammonia gas in a 4.32 liter container at 837 torr and 45 degrees Celsius is blank grams per milliliter. So our equation for when we're dealing with densities is pressure times the molar mass is equal to the density times R times T in Kelvin. Now let's see, we're solving for density here, so the density is going to be equal to the pressure times the molar mass over RT. Okay, so my pressure, I've got to convert from 837 torr to atmospheres, and that's going to be 1.10 atmospheres. Okay, my molar mass there, since it's ammonia, that's NH3, that has a molar mass of 17 grams per mole. And then R, I'm not going to write out all the units because I'm not going to have room. And then temperature, we've got to do that in Kelvin, and 45 degrees Celsius becomes 318 Kelvin. And when we work all of that out for our density, we get a density that's equal to 0.717 grams per liter. Okay, so that would be A. Okay, so it's not a hard problem to do, but there's a lot of places to make mistakes. You've got to remember to convert your pressure into atmospheres. For this one, you've got to know what ammonia is. Not a test, I would have told you it was NH3. Figure for the practice, you can always look it up. R is a constant, but then you've got to remember to convert your temperature to Kelvin to get all your units to work out. So, like I said, not a hard problem once you have all the numbers in place. But getting those numbers in place, lots of places to make mistakes. Any questions on that one at all? Turn autofocus off. There we go. All right, number 9. Yeah, okay. So here we're given a sample of gas at 2.49 grams. The volume was 752 milliliters. At 1.98 atmospheres and 62 degrees Celsius. The gas is what? So for this one, we got a couple of different ways that we can work that one. We can figure out how many moles of gas there are, and once we figure out how many moles there are, we know how many grams we have. We can figure out the molar mass, or we could actually use the mass of the gas present, convert the volume into liters and get a density and use the previous equation that we just used. Either of those things will get you the exact same answer. Let's just work it out the first way that I mentioned. So we'll solve for N here because we know we've got PV equals nRT. We know the pressure. We know the volume, we know the temperature, so we can solve for the number of moles. So N is going to be equal to PV over RT, and so
Our P is equal to 1.98. Our volume is, again, you got to make sure that you put this in liters, so 0.752 liters. And my R, of course, is a constant, 8.206. And then my temperature here, it's 62 Celsius, so we've got to convert that into Kelvin. And that's going to give us what? 335 Kelvin. Okay? So that's equal to N. So when I solve for N here, I get 5.42 times 10 to the minus 2 moles. Okay, so that's the number of moles I have present in my sample, and that many moles weighs 2.49 grams. Okay, so we know molar mass is equal to grams over moles, so I can do 2.49 grams over 5.42 times 10 to the minus 2 moles, and I'm just doing this strictly from a unit standpoint. We know molar mass is grams per mole, so let's put our number of mass, or our number of grams, over the number of moles. And when we do that, we get a value of 46 grams per mole, and the only gas in here that has that mass is going to be C and O2. O2 is 32, nitrogen is 14, that gives us 46. Like I said, you also could have worked that one from the density equation using the mass and the volume that was given and going from that standpoint. Okay, any questions on that? Okay. Yeah, that's the thing about a lot of these problems is there's a lot of ways to work them. There's not one way that it has to be done that way. A lot of different ways to look at these. Number 10, I'm not even going to ask because I had a few people ask me about that one today, so I'm sure there's questions on it. So for this one, the volume of HCl gas required to react with excess magnesium metal to produce 6.82 liters of hydrogen gas at 2.19 atmospheres and 35 degrees Celsius is blank liters. So the first thing that we've got to do with this one is write out a reaction. We're given the reactants. We've got HCl in a gas form plus excess magnesium metal, so we're reacting it with magnesium. It's going to produce hydrogen gas, which is H2. You got to know that hydrogen's diatomic, so it's going to make H2. And then the last product isn't terribly important, but magnesium and chlorine are going to combine to make magnesium chloride, MgCl2. And then when we balance it, we need to put a 2 there to balance the hydrogens, and then that also balances the chlorines over here, which isn't all that big a deal for our problem. Okay, so there's a couple of different ways that you can solve this problem. The quick way, if you recognize this, okay, and this is not an expectation, but I know that some of you out there are extremely sharp and you can recognize some of these things immediately. We see that we have a 2-to-1 ratio for HCl and H2. Okay, well, since the conditions don't change, that means that the amounts of gas are going to be determined strictly by the number of moles required. So if I am making 6.82 liters of hydrogen gas, and for every 1 mole of H2, I need 2 moles of HCl, that means I need twice the volume. So it's going to need twice 6.82, which is going to give you 13.6. Okay, that's the quick way. Okay, but I don't expect all of you to be able to look at that problem and know that that's how you're going to do it. So let's look at it the more methodical way and think of a way that you might do it that might make a little bit more sense. Okay, so let's just look at our H2 first, because that's what we have all of our data for. Okay, so we can look at it as PV is equal to nRT. Let's solve for how many moles of H2 that we have to have. That's going to be equal to PV over RT. Our pressure was 2.19 atmospheres. Our volume was 6.82 liters. Our R is 0.08. I'm just going to start writing that as 0821. And then our temperature there is 308 Kelvin. So when we work that out, we get 0.591 moles of H2. Okay, so based on the information that the problem gave me, that's the number of moles of H2 that was made by the reaction. Okay, that's strictly just using ideal gas law and the data given by the problem. Okay, now when we look at this reaction here, I've got 0.591 moles of H2. I know that it takes 2 moles of HCl for every 1 mole of H2, and that's given by the stoichiometry, and so that means I'm going to need 1.18 moles of HCl. Okay, so now we can work that out for our HCl here, and we know the number of moles. And so, again, we're going to work PV is equal to nRT, except now we know the number of moles. What I'm looking for is my volume, which is going to be nRT over P. And so that becomes 1.18 times 0.0821, my value for R. My temperature is still the same at 308. My pressure is still the same at 2.19. And when I work out that volume, I still get 13.6 liters. Okay? So, kind of what I just said, there's a lot of times there's more than one way to work these problems. Okay, sometimes you can just kind of intuit them through, but I know for some people that's not an option, and you may just need to do the brute force and work it through like that. There's nothing wrong with it. It's fine. Okay? I would expect more of you to work it through this way, because that's the way we've talked about doing it in class. Okay, questions at all on that one? Any questions there? All right. Oh, let's see. Number 11. Yes. Kind of expected that one too. All right, so number 11. Pressure in a 12.2 liter vessel that contains 2.34 grams of carbon dioxide, 1.73 grams of sulfur dioxide, and 3.33 grams of argon, all at 42 degrees Celsius is what millimeters of mercury? So we're going to calculate the pressure. We're going to use the ideal gas law. We're going to end up calculating the pressure in atmospheres, and then we need to convert that into millimeters of mercury. So the one thing that we need to kind of look at here, we've got a volume that's equal to 12.2 liters. I've got a temperature that's equal to 42 degrees Celsius, which is equal to 315 Kelvin. We're looking for pressure. Now the key here is our number of moles, okay? Because we're not given moles, but we're given a lot of different grams for a lot of different substances. So our N is going to be the number of moles of carbon dioxide, CO2, plus the number of moles of sulfur dioxide, SO2, plus number of moles of argon. Okay, because ideal gas law, it doesn't care what gases are present, just how many moles of gas are present. Okay, so we need to go through and convert all of those, and for whatever reason, I don't have all those calculations done on my sheet. We must have just talked through them the last time I worked this one. Okay, so let's go ahead and do this. So number of moles of CO2 is going to be equal to 2.34 grams times 1 mole per 44 grams. I have no idea what that comes out with. So that comes out to be 5.32 times 10 to the minus 2 moles. Our number of moles of SO2 is going to be, how many grams there? 1.73 times 1 mole per I'll say about 64 grams. That's 2.70 times 10 to the minus 2. And then number of moles of what? Argon. It's going to be equal to 3.33 grams. 1 mole per argon is about 40. So you get 8.30 times 10 to the minus 2 moles there. So when we add up our total number of moles, when we add up our total number of moles there, we get 0.1635 moles. And I'm not going to go through and do the rest of that because I think we've done ideal gas law to death in the last 15 minutes. But we've got number of moles now. We're going to find a pressure. We've got temperature. We've got volume. Again, the pressure that we're going to find here with PV is equal to nRT. You're going to solve for pressure there. The pressure value you get is going to be in atmospheres. So you just need to convert those atmospheres into millimeters of mercury using the 760 millimeters of mercury per atmosphere conversion. Questions at all? Questions there? All right. Number 12. Yeah, okay. I'm guessing there's not going to be a whole lot that we're not going to talk about tonight. So number 12, in a gas mixture of helium, neon, and argon with a total pressure of 8.4 atmospheres, the mole fraction of argon is what if the partial pressures of helium and neon are 1.5 and 2 atmospheres respectively. Okay, so remember that the partial pressure of a substance, so partial pressure of A, would be equal to the mole fraction of A times the total pressure. Okay, so if we're solving for the mole fraction, that's going to be equal to the partial pressure of that substance over the total pressure. Okay, so when we look at helium and neon, they're occupying 1.5 and 2 atmospheres. So they've occupied 3.5 of the atmospheres. So the partial pressure of argon here, argon, is going to be equal to the total pressure minus the partial pressures of the other two. So that gives us 4.90 atmospheres. Okay, so argon is going to have a partial pressure of 4.9 atmospheres. And then if we look at our mole fraction of argon, that's going to be equal to its partial pressure, 4.9 atmospheres over the total number of atmospheres, 8.40. And when we calculate that out, we're going to get 0.583. Okay, does that make sense? We're just looking at what portion of the pressure is occupied by the argon, and that's going to be equal to its, however, the same fraction of the number of moles that it has present. Because again, the gas pressure doesn't really care what gas identity it is, how much of it is there. Mole fractions have no unit, because it's atmospheres over atmospheres. All right. Number 13. Yes? So 13 is A there. Kinetic molecular theory assumes, so the correct answer is A, gases consist of tiny particles in constant random motion. That's pretty vague. Let's take a look and see what's wrong with the other answers there. Collisions between gas particles are inelastic. Okay, for collisions that are inelastic, that would mean that they lose energy every time they collide. Well, when you got things moving 500-600 miles an hour, they're colliding a lot, and they would lose energy with every collision. They would eventually slow down, stick together, everything would become a liquid or even a solid. And we know that that doesn't happen. So that's why B is not correct. Average kinetic energy of the particles of the gas is directly proportional to the centigrade temperature. I haven't seen the word centigrade in a while. That's the same thing as Celsius, in case you're wondering. That's not true. It's directly proportional to the what temperature? Kelvin temperature, absolute temperature. Attractive and repulsive forces between gas particles are stronger than those between gas particles and container walls. When we were dealing with ideal gases in kinetic molecular theory, what did we say about attractive and repulsive forces? We said there wasn't. Okay, otherwise they start sticking to things. Okay, and that was an approximation to keep them from changing paths and keep them from sticking together. Okay, and then of course E isn't true at all because they're not all true. Okay, so A is the correct answer there. Again, it's a pretty vague answer. For questions on the exam, we would try to have something that's a little more specific than that. All right, number 14. Yep. Okay, I don't think there's much to work out with number 14. So the following gases, which will have the greatest rate of effusion at a given temperature? So remember that effusion is controlled by the molar mass, and so the smaller the molar mass, the greater the effusion rate is going to be. So really what you're looking for is the lightest molecule in here, in terms of molar mass. So HCl would be 36, NH3 would be 17, CH4 would be 16, argon is going to be 40, and HBr is just going to be huge. I'm not even sure what it would be off the top of my head. It's going to be 81. So the lightest, the smallest molar mass is going to give you the greatest rate of effusion. So the answer for 14 should be C, and it is. Okay, so rates of diffusion controlled by molar mass. All right, number 15. Yep. So, tank containing both HF and HBr gases developed a leak. The ratio of the rate of diffusion of HF to the rate of diffusion of HBr is what? Okay, so we want to look at our effusion here. So if we want to look at the rate of effusion of HF over, man, you guys got the hacky gackies out there, over HBr, all kinds of sickness going around. Okay, so that's going to be equal to the square root of the molar mass of HBr over the molar mass of HF. So the molar mass relationship flip-flops because it's a 1/over relationship from what we have for that rate. And so now what we just do is plug in our values now. So the molar mass of HBr is 80.9. Molar mass of HF is about 20. We divide those, we take the square root, and we get 2.01 there, and it's not going to have any units. And what that means is that the HF will effuse about twice as fast as the HBr does. Okay, so it's going to come through, it's going to leak through a very tiny hole about twice as fast as the HBr. It's a smaller molecule, it's moving quite a bit faster, so it has a lot more opportunity to get through that hole. Right, questions on that one at all? Feels like forever ago that we looked at this stuff, doesn't it? All right, number 16. Yep, okay, so for 16, all we're doing for 16 is looking at molar masses. So let's just write out the different compounds there. We've got He, O2, CO2, and N2. If we look at their molar masses, it has a molar mass of 4, O2 is 32, CO is 44, N2 is 28. Okay, so the smaller they are, the faster they're going to go. Okay, because remember, your temperature is a measure of the kinetic energy, which is 1/2 mv squared. So if they all have the same basic kinetic energy, a lower mass is going to need a higher velocity. Okay, so if we're just looking for average molecular speed there, so the slowest one we want to go first. Increasing, so we want the slowest one first. So the slowest one is going to be the heaviest one, CO2. The next slowest, the next heaviest, O2. And then N2. And then HE. So that would be A. There we go. Hopefully that's the answer. And it is. Okay, questions at all on that? Taking us a little while to get through these. Let's see here. Number 17. Okay, we don't really do much with the real gases. We certainly don't do any calculations, but it is important to know the differences between them. And the main thing, well, there's lots of things in there actually that I would say are probably the correct answer. We do consider the volume of real gases, which is why there's a correction to the volume variable in a real gas equation. So I would consider B to be correct, and I would also have to consider D to be correct as well, because we do have to factor in any attractions between those. So it's not a particularly good question that came out of the test bank. So I would consider either B or D to be correct there. All right. 18, that's just a definition on the constant sheet that's on the back. I'm not going to go over that one. Let's see, how about 19? Do you guys remember the easiest way to recognize a state function? Your state functions are stated in capital letters. Yeah, that's it. Non-state functions are lowercase, state functions are uppercase. Okay, so that's why Q and W in heat are written in lowercase, and H, enthalpy, is written is in uppercase H. Okay, all your state functions are written in uppercase, all your non-state functions are written in lowercase. It's that easy. So. Let's see, number 20. Yes. So, number 20 says, what is expected when the combustion reaction shown below takes place in a thermally insulated container? Okay, so that means that heat's not going to be going out to the atmosphere. Outfitted with a movable piston at constant atmospheric pressure. Okay, so since imagine that we have a container and we are going to cause a small explosion in it. Small. Okay, and the piston can move because we're at constant pressure. So what's going to happen with that container as far as the volume? I have a container here and a small explosion happens. What happens to the volume? Yeah, it's got to go up. So we know volume's going to increase. That takes out C and D. Okay? Now, work. So as the system is moving that piston, is it doing work or is it having work done on it? Could I attach something to that piston and have that explosion move it? I certainly could. That's how your car works. You have a little container in there where gas explodes and it pushes a movable piston up. It drives a crankshaft and makes your cars go. So I know it's a little more complicated than that, but that's about the extent of my mechanical knowledge. So it's doing work. Okay, it's doing work. The system is doing work. It's not having work done on it. If I were compressing that gas, then I would be doing work on the system. But since the gas is expanding against atmospheric pressure, it is doing work. So work is done by the system. So the correct answer there should be A, and it is. Questions at all on that one? Yeah, for those of you going to be engineers, you're going to get sick of looking at heat and work, but you're going to see a lot of it. When you take engineering, thermodynamics. The horror. I had to take that. Let's see. Number 21. Yeah? Okay, so there we're just looking at signs and terms. Okay? So if we have a negative delta H, is that endothermic? It's not, so A is not correct. If I have a negative delta H, is that exothermic? Yes, and so that's why B is correct. C says a positive delta H, is that exothermic? No. Positive delta H is what? Endothermic. And then the 0 delta H, that's nothing. That's actually a term that they used in the next problem down that I don't know if I've ever seen in a book before, is equithermic. It just means that there's no heat transferred at all. It's a zero heat transfer process, which are really rare. They do exist, but they're really rare. So the correct answer there would be B. Negative delta H, exothermic. Positive delta H, endothermic. All right. 22. Well, 22 is just like 21. If the delta H is negative, it means the process is exothermic. There we go. That was easy. All right. 23. Yeah, we'll just do it because it's easy to talk about. So 23, we see that we have a delta H that is negative, so that means it's what? Exothermic. And is heat absorbed or released? It's released. Easy way to remember that, heat is going out. Exothermic. Exit heat. Exit, exo. Okay, so heat is exiting, so heat is being released by the system. Exothermic. Good. Let's see, 24. Yeah? Okay, so 24. Value of delta H for the reaction below is negative 126 kilojoules. How much heat is released when 2 moles of NaOH is formed in the reaction? So let me write out the reaction here. This stuff there, Na2O2, it will react with moisture in the air quite violently and create a lot of heat. It does not play well with water. When I was a college student, chemistry major, my sophomore year, we used sodium. This is sodium peroxide. It's like hydrogen peroxide, but with sodium instead. And it's something that's called pyrophoric because it just tends to catch fire in the air, and that's because of the water in the air. We used it for different things. It's a great compound for doing reactions for some things. But we had a chem major, he was a bit of a klutz, and he had spilled some of it. Not a big deal. He cleaned it up with a paper towel, and he threw it in the trash right next to me. About 5 seconds later, woof, complete column of flame about 8 feet high. That was exciting. I still remember that. That was a lot of years ago. He did not finish as a chemistry major. He had a few other incidents that year. One thing he did led to an acid spillage that started to dissolve the file cabinet. Yeah. He became an English major. That was a much better place for him. Books don't catch fire too much. All right. So, we know the value of delta H for this one is negative 126 kilojoules. Okay, and so we know that we get that negative 126 kilojoules for 4 moles of NaOH. So we can say negative 126 kilojoules per 4 moles of NaOH. So how much heat am I going to get out when I do 2 moles of NaOH? Well, you can do the cross math if you want, or you can just look at it and say, well, if I'm going to get half as much material out, I must have put half as much material in, and it's only going to make half as much heat. So my delta H for that would be negative 63 kilojoules. Now you look on there, it's like there is no negative 63 on here. Well, that's because of the wording of the problem. It's very important. Okay, the important thing to remember about heat is there's no such thing as negative heat. There's only heat. It only has a positive value. Okay, the positive and negative that we put in front of the heat value just tells us the direction of flow. Is that much heat flowing into the system, or is that much heat flowing out of the system? We were already told that the system is releasing heat. It says how much heat is released when this happens. And so the negative is already implied by the wording of the problem. And so we're actually releasing 63 kilojoules of heat. If it said what is the delta H for that much NaOH being produced, then you would need to say negative 63, because you need that negative to imply which direction heat is flowing. But since the wording already said that heat's being released, we only need the value, which is the 63 kilojoules. Does that make sense? It's a lot like money. Okay? And you say, what's the flow of money when you buy something? Well, it's going to be negative $5 because I'm losing $5. As opposed to somebody says, well, how much is that going to cost? Well, if something costs you something, you know how it's flowing out, and then you can just say $5. I don't know if that's a good example or not. You get the idea. All right. 25. Yep. Okay, 25 is very much the same kind of problem. We were given a problem, and we're told that releases a certain amount of heat, and then we're given an amount in grams, and asked, well, how much heat is that going to release? Then it just becomes a proportion. So we know that for this reaction here, we have CH4 plus 3 Cl2 goes to CH, Cl3 plus 3 HCl. See if I've got this one written out. Yep, I do. And so I know that releases 336 kilojoules of heat. Okay, so that's negative 336 kilojoules per every 3 moles of HCl. So for every mole of HCl that gets produced, I release 112 kilojoules per mole of HCl. And then if I convert that number of grams, 23 grams, into moles, it turns out to be 0.63 moles of HCl. And so when we work that out, we get a negative 70.7 kilojoules. And again, the wording says calculate the heat released. And so we're only looking for that value there, 70.7 kilojoules. So that's how much heat would be released when I make that many grams of HCl. It just becomes a proportion of what the problem says. Man, we got a lot of problems on here. Holy smokes, we got a lot of problems on here. Let's see. The exam only has 26, so don't worry if you couldn't finish this one very quickly. Yeah, sorry. 336 divided by 3. Yeah. Let's see. Number 26. Pretty good, okay. 27. Yes? Okay, 27 says temperature of a 15-gram sample of lead metal increases from 22 degrees Celsius to 15 degrees Celsius upon the addition of 29 joules of heat. The specific heat capacity of the lead is what? So for this one, we know that, let's see, what number is that one? 27. So I know that heat is equal to mass times specific heat times my change in temperature. The amount of heat that was absorbed here was 29.0 joules. The mass of the sample was 15 grams. We're looking for the specific heat, C, And the change in temperature, so it went from 22 to 37, and so that was 15 degrees Celsius. And so when I solve that for C, what do I get? I get 0.13 joules per gram degree C. So that should be A, which it is. Questions all on that one? Yep. Okay, well that's going to be the same. Because your temperature difference in Kelvin and Celsius is going to be identical because their scales are exactly the same size. So I hadn't seen that. So this would actually be 15 Kelvin for the difference in temperature. And then your unit works out right. I try not to do that either to you guys. Alright, so that was 27. Let's see, 28. Is that a yes? Alright, so 28. So let's see, so we got to figure out what we can do to these two equations to get the third equation, or to get that top one there. Okay, so let's see. We've got to... our top one has IF3 in the products, and that's the only one that's got IF3 in the products. So we've got to leave that one alone. So we're going to have IF, this is number 28. We're going to have IF plus F2 going to IF3. And that's got a delta H negative 390 kilojoules. And then my second equation has IF5 as a product. I've got to get it as a reactant, and there's just one of them, each one, so I can just swap that around. So that's going to give me IF5 goes to IF plus 2F2, and because I flipped that one around, I just changed the sign of the heat involved. And so we see that our IFs cancel here. Our F2 there cancels, and the part of the F2 there cancels. That leaves me with IF5 goes to IF3 plus F2. That's the correct reaction. And when I add all of those temperatures together, I get a delta H that's equal to positive 355 kilojoules. There's lots of different ways to work those, lots of ways that they can be given to you. You've just really got to make sure that you've got all the parts and pieces that are there. One of the easiest things to look at first, do you have anything unique in each reaction to see where it's got to be placed in reactants or products, and how many of them do you need? Okay, and then if you've got other reactions in there, you may need to manipulate them to see if you need to cancel something out. Okay. All right. That's 28. Number 29 is pretty much the same kind of deal. I'm not going to go through that one just in the interest of time. What are you going to do with number 29? I'll let you just look at that. What are you going to do with the first one? Yeah, you've got to leave it because you've got N2 as a reactant, and the one you're trying to end up with has N2 as a reactant, and that's the only N2 anywhere, so that's got to stay the same. And then what do you got to do with the second one? You got to flip it because it's got two NO as a reactant, and you've got two NO as a product in your final reaction, and so those have to be moved to the other side, so you've got to flip that reaction in. Good. Good. Let's see, number 30. Yes. So number 30 is really just looking at, do you know the definition of a heat of formation reaction? Okay, so the heat of formation reaction requires that you're making 1 mole of your product in its standard state from its components in their elemental states. Okay, so there's some things that we can throw out there. If we look at A, some of the problems there in the reactants, it's got H is a gas and Br is a gas. Well, those are 2 diatomic elements, so it should be H2 and Br2. So that's out. B looks good because it's got H2 and N2 in their elemental states, but it's making 2 moles of NH3. The formation reaction is always making only 1 mole of product, always. So B is out. C looks really close. A couple problems there, though. Is carbon normally in a gas phase at room temperature and pressure? It's not. It's not a gas. That's why we have charcoal briquettes. That's carbon. And also it has oxygen just as O, when it should be O2. So that's not good. And then D is the correct answer. We're making 1 mole of NO2 from half a mole of N2 and a mole of O2. Okay, so that's our correct answer there. And then E has the same problem with the hydrogen. It's just H. It should be H2. All right, so that's what that one's checking there. 31. 31, yes. Okay, so 31, looking for a heat of formation. So remember, a heat of formation value is 0 for something in its elemental standard state. Okay, it's standard elemental state, a better way of saying it. Okay, correct answer there is D, F2, because it says it's a solid. What is F2 at room temperature pressure? It's a gas. Okay, it's fluorine gas. Okay, it's not a solid, it's a gas. Okay, just like chlorine and bromine, all those guys there. Okay. All right. Let's see, 32. Yes? Okay, so 32, we're just looking for the delta H reaction there. And so remember when we're doing these, it's just kind of an extension of Hess's law. We're just going to look at the sum of the delta HFs of the products minus the sum of the delta HFs of the reactants. Okay, and we use the coefficients as multipliers here. So we're going to take our calcium arsenate there. So we've got just one of those. So it's going to be delta H reaction is going to be equal to negative 2346.0 plus our 2 waters there. So that's going to be 2 times negative 285.9. Okay, so there's the sum of my products minus the sum of the reactants. So that's going to be my calcium hydroxide, negative 986.6, plus, I've got 2 of the arsenic acids here, 2 times negative 900.4. Those are all in kilojoules. And when you do that long, drawn-out math there, what do you get? You get a negative 130.4 kilojoules. Whew. Okay, so for your delta H reaction, you're given those delta HFs, the sum of the products minus the sum of the reactants. More. Okay, 33 is very much similar. The only difference there is that you're given the delta H of reaction, but you're not given one of the components, so you just need to solve for it. Again, in the interest of time, I'm not going to go through that one because I want to get to some of the other ones here. All right, 34. You guys good at 34? Excellent. That's just bonds broken minus bonds formed. All right, the last ones I wanted to get to are some redox problems because we haven't done any of those for a while. Redox is on this test. So let's see. So for number 1, it says, which atom in the compound K2C2O4 has a positive oxidation state? Okay, so we have K2C2O4. Okay, so we go through our set of rules. Anything in elemental state gets a 0, while this is a compound, so nothing's in the elemental state. If we have any oxygens, we assign it a -2. So the oxygen gets a -2. There's 4 of them. So there's a sum total of a -8 for the oxygen. Any hydrogens get a +1. There's no hydrogens. Any group 1As get a +1. We do have 1A. We get a potassium there, so that gets a +1. There's 2 of them there, so that's going to be a +2. Okay. And any group 2 elements get a +2. There's none of those. Any monatomic ions, well, again, we have a compound. And so now we've got to get the sum of the oxidation states to add up to the overall charge, which here is 0. So what do I need to add to a +2 and a -8 to get to 0? +6. So that's the total of the carbons. Each carbon then must be a what? +3. Okay, so now we've assigned oxidation states to all of those species. We want to know which has a positive oxidation state, and we find that it is the potassium and the carbon that have positive oxidation states. So that would be B. Okay. Questions there at all? It was still October when we were covering this stuff. We covered this stuff on Halloween. All right, number 2. Which of the following is true for the following reaction? So here we've got a reaction. Copper plus zinc chloride goes to copper chloride plus zinc. We can assign oxidation states. We've got a couple things in elemental state here, the copper and the zinc. We go all the way through the list of rules, and none of them apply. And we can't, even when we get to Rule 7, where it says the sum of the oxidation states have to add up to the overall charge, well, I still don't have anything for the zinc or the chlorine, so I can't even assign those yet. Okay, but if we can't do anything with Rule 7, then we go to Rule 8 that says if you haven't assigned an oxidation state to a halogen yet, give it a -1. And then go back to Rule 7. So now we can assign the chlorines a -1 here, and that gives them a -2, a -1, total of -2. And that allows my zinc to be a +2, and the copper over here to be a +2. All right, so now we've assigned oxidation states to everything there. So now we want to know which of the following is true. Okay, is copper serving as a reducing agent? Okay, so here copper is going from a 0 to a +2, so what's happening to it? It's being oxidized, which means it is the what? It is the reducing agent. So A is true. Is copper oxidized? Yes, that is also true. Zn2 plus is reduced. Yes, because Zn went from a Zn +2 to a Zn0. So that was reduced, which means that D, all of those statements are correct. Okay, all of those statements are correct. Well, let's see. 3 is just a nasty problem. I'm not going to go through number 3 because I'm not going to give anything quite that weird on the exam. Because you've got leads coming from 2 places and ending up in 1 place, and that's what makes it a little bit strange. But let's take a look at number 4 there. I guess I don't have much to write down. So let me give you a little bit of a clue on how to do a problem like number 4. Okay? And really easy, and this doesn't always work. This is just kind of, take your first shot at it, and if it comes out this way, great. If not, you're going to have to do it through the brute force method. But it says, which of the following is not an oxidation-reduction reaction? You might think that you have to go through and assign oxidation numbers to every single thing in every one of these reactions to figure out which one of those is not a redox reaction. Okay? And that's kind of the last resort. Something you can do before that, okay, is to look at the elements that are present in the reactants and products of each reaction. If you have something that's going from an elemental state to a compound, so elemental state in the reactant to a compound in the product, it's a redox. Or vice versa. If you have something in a compound in a reactant and then it goes to elemental state in the products, it's a redox reaction. You can just assume that's a redox reaction. Okay. If everything is in compound on both sides, it's more complex. Okay. But if you have anything go from elemental to compound or compound to elemental, it's going to be a redox reaction. So if we use kind of that reasoning, if we look at A, we have magnesium elemental state going to MgCl2. That's a redox reaction. For B, we have oxygen O2 going into CO2 and H2O. Elemental state going to a compound. That's a redox reaction. C, everything is in a compound. Hard to say anything about that. But D, we have sodium going from elemental state to a compound. That's a redox reaction. So A, B, and D are all definitely redox. So by elimination, you can say that C is not. You can go back and verify that redox. All right. Nice job tonight.